Imagine standing in space, perfectly safe inside your spacesuit. And then, without any warning, the atoms in your body start getting pulled apart. Not by gravity, not by heat, but by a magnetic field so violent it can literally shred matter from a distance. We're talking about the universe's most dangerous magnets, magnetars, and the extreme magnetic fields around them that can rip atoms apart like tissue paper. Picture a star bigger than our sun, living fast and dying young. For millions of years, it burns furiously, fusing hydrogen into heavier elements, climbing the periodic table like a cosmic ladder. But once its core fills with iron, the game is over. Iron doesn't give energy when fused, so gravity suddenly wins. In a fraction of a second, the core collapses under its own weight, cramming more mass than our sun into a sphere about the size of a city. The outer layers rebound, a titanic explosion rips through space, and a supernova lights up its galaxy like a flashbang. What's left behind can be a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons. But under the most extreme, chaotic conditions during that collapse, rapid spin, a superfluid interior, and a magnetic dynamo cranked to maximum, you get something even more terrifying: a magnetar. And this is where violent magnetic field stops being a dramatic phrase and becomes a literal threat to the structure of atoms. A magnetar's magnetic field can reach up to around 10 to the power of 14 to 10 to the power of 15 Gauss, making it the most magnetic kind of object known in the universe. For comparison, Earth's magnetic field is about 0.5 Gauss. Your fridge magnet might be 100 Gauss. A powerful MRI machine in a hospital is maybe tens of thousands of Gauss. A magnetar laughs at all of that. Its field is roughly a quadrillion times stronger than Earth's. Here's a simple way to feel how insane that is. A magnetar's field could erase every credit card on Earth from halfway to the moon, and it could distort atoms from hundreds of thousands of kilometers away. You don't have to touch it, you don't even have to get close in the normal sense. Just entering its magnetic influence is like walking into a shredder designed for matter itself. So how exactly does a magnetic field, something invisible and intangible, rip apart the building blocks of reality? Under normal conditions, an atom is a delicate balance. You have a positively charged nucleus in the center and negatively charged electrons in fuzzy three-dimensional orbitals around it. Quantum mechanics spreads the electrons out into these cloud-like shapes, and the electric pull between nucleus and electrons defines the atom's size, shape, and chemistry. That's the calm, ordinary universe, what you and I live in. Now throw that atom into a magnetar-strength magnetic field. Suddenly, the magnetic pressure is not some gentle background factor. It becomes the dominant force. The field grabs hold of the electrons and clamps them down along the direction of the field lines. The nice, roughly spherical electron cloud collapses inward and stretches into an ultra-thin, elongated shape, like the atom has been crushed into a microscopic needle. Calculations show that once you go above about 10 to the power of 9 Gauss, atoms start to deform noticeably. By around 10 to the power of 12 Gauss, a trillion times Earth's field, even hydrogen, the simplest atom, becomes a strange, tightly bound filament. Push it all the way to magnetar levels, near 10 to the power of 15 Gauss, and the energies involved become so extreme that the usual rules of atomic physics start to break down. At that point, the field can overpower the electrostatic forces holding electrons to nuclei. Electrons are ripped out of their orbits. Molecules are torn apart. Matter is ionized and shredded into a sea of particles. This doesn't need you to be touching the star's surface. This can happen thousands of kilometers away. Imagine a spaceship that dares to fly near a magnetar. Long before it crashes into anything, its atoms are under attack. The magnetic field starts stripping electrons off the hull, turning solid metal into a super-hot plasma, atom by atom. Electronics die first. Data gets erased. Circuits short and melt. Then the structure itself weakens as chemical bonds. just arrangements of electrons, are broken by the field. Eventually, there's no spaceship, no crew, just a spray of ionized particles forced into alignment along invisible cosmic rails. Now imagine watching that from a control room light years away, your instruments going off the charts as the ship's signal turns into pure static. 1 second you're tracking a healthy spacecraft, the next second its entire mass is being reorganized by an invisible force you cannot shield against. No impact, no explosion, just a slow, unstoppable unmaking of matter. The only trace left is a faint, ghost-like glow in X-rays and gamma rays, a kind of cosmic death certificate written in high-energy light. In human terms, it's the closest thing to watching reality itself glitch and tear. And if you somehow floated there without a ship, your body is basically complex chemistry held together by electromagnetic forces. A magnetar doesn't care. It would start to pull apart the atoms in your blood, your bones, your brain. The same magnetic violence that distorts atoms on the star's surface would begin re-sculpting the matter that used to be you. But magnetars don't just torture matter. They also twist space itself into something weirder. At these field strengths, even the vacuum, the empty space around the star, stops behaving like nothing and starts acting like a strange medium. Light traveling through this environment can split into two components, each polarized differently, as if the vacuum had become a crystal bending and splitting beams. This phenomenon, called vacuum polarization, is something we can't reproduce in any lab on Earth, but magnetars do it effortlessly. The magnetic field can also accelerate particles to near light speed, turning the region around a magnetar into a natural particle accelerator far beyond what our machines can achieve. Electrons and their antimatter twins, positrons, spiral along the field lines, collide, annihilate, and release bursts of high-energy radiation like X-rays and gamma rays. Some magnetars are associated with intense gamma-ray bursts and fast radio bursts, mysterious cosmic flashes that can momentarily outshine entire galaxies. Now here's a detail that makes these things feel even more alive. Some magnetars aren't just sitting quietly in space. Astronomers have found magnetars like SGR 0501 plus 4516 literally racing through the galaxy at more than 100,000 miles per hour, like a rogue cosmic bullet carrying its weaponized magnetic field wherever it goes. If one of these ever happened to pass a little too close to a planetary system, it wouldn't need to collide with anything. The radiation and magnetic chaos alone would be enough to rewrite the local environment. So where does all this magnetic violence come from? Inside a newborn neutron star, you have a rapidly spinning, incredibly dense core with matter in exotic states, superfluid and superconducting. This combination acts like a colossal dynamo, a generator on steroids that amplifies the star's original magnetic field to mind-bending levels. While an ordinary neutron star might have a field around 10 to the power of 12 Gauss, a magnetar can be 1,000 times stronger. Once this field is locked in during the early evolution of the star, it becomes the defining feature of its life. But the story doesn't end with a static supermagnet sitting there. Over time, the magnetic field stresses the solid crust of the magnetar, twisting and distorting it. The crust resists for a while, storing enormous tension, until it suddenly snaps in what scientists call a starquake. When that happens, it's not a gentle crack. It's more like a planet-sized slab of ultra-dense material shifting abruptly. The magnetic field lines anchored in that crust are forced to break and reconnect, a process called magnetic reconnection, similar to what powers solar flares on the sun, but multiplied by 1 trillion. In an instant, stored magnetic energy is unleashed as a catastrophic flare. First, there's a blinding initial spike, a burst of gamma rays and hard X-rays that can last mere milliseconds but carry an enormous fraction of the total energy. Then comes a decaying tail, an afterglow that can pulse for hundreds of seconds as hotspots on the magnetar's surface spin in and out of view. The star literally rings like a bell, shaking from the seismic waves triggered by the quake. We've detected such flares from magnetars in our own galaxy, and even from tens of thousands of light years away, they can briefly dominate the gamma-ray sky. One famous magnetar, SGR 1806-20, released a flare so powerful that, if it had been much closer, it could have seriously affected Earth's atmosphere, ionizing parts of the upper layers and subtly disturbing our planet's magnetic environment. That happened from about 50,000 light-years away. Imagine the same event at a fraction of that distance. Now, what if a magnetar actually came close to our solar system? We're lucky. The known magnetars are safely far away, scattered across our galaxy. But let's say one wandered to within a few light-years. Even then, the biggest impact might be subtle. Changes in high-energy radiation, some extra cosmic fireworks in our skies. But if it came dangerously close, say within a fraction of a light-year, the story turns into cosmic horror. At large distances, its radiation could strip away parts of Earth's atmosphere, damaging the ozone layer and showering the surface with harsh radiation. Closer in, the magnetic field could wipe out electronics, disrupt planetary magnetic fields, and bathe planets in intense X-rays and gamma rays. Go closer still, and you're in the zone where the field begins to rip apart matter itself. In that region, atoms no longer behave like atoms. Everything you know, rocks, water, air, your own body, gets turned into stretched, distorted, and finally shredded matter, without ever laying a finger on them. If you want to keep exploring these extreme corners of the universe, the stars that tear atoms apart, the black holes that bend time, the cosmic phenomena that make our everyday reality look fragile, make sure to stick around, subscribe, and share this video with someone who thinks magnets are no big deal. Because out there, in the dark, the universe is just getting started.